I'm Juan Pablo Ulberich from Argentina. I'm going to present this presentation titled Unveiling Geothermal Resources, an analysis of heat flow anomalies in Northwest Argentina, in the back arc of Northwest Argentina, using oil and gas well data. I'm an assistant researcher of the CONICET, the National Council of Scientific and Technical Research of Argentina. I'm part of the research group of magmatism and associated geological energy resources. This presentation is in the frame of the Cuya CONICET project, a cooperation project between Italy and Argentina, that in the beginning, the idea was to use the CO2 flow as a tool for geothermal investigation, but we cannot apply this method because there is no CO2 in the basin. So we use the pre-existing data from gas and oil exploration to analyze the variations in the geothermal gradients, identify potential fluids, and indirectly infer the thermal conductivity and the heat flow because we have no access to the sample cores to make direct measurements, and there doesn't exist thermal conductivity measurements for the basin. And the main goal of all this study was to understand the spatial variations and geological control on the heat flow. Well, to introduce quickly the regional setting, we are in the Central Andes. It's an area in the center of South America, the west central of South America, where the Nazca plate subduct beneath the South American plate with a normal angle. Is the area of the Andes where the width of the Cordillera is around 800 kilometers. It's characterized by the Altiplano Puna Plateau, 3,600 meters plateau above the sea level, limited to the west for the forearc and the actual volcanic arc, and to the east for the Foreland or the back arc, the area where is our study location. Where here are a map with the different geological provinces. We are located in a transition between a normal foreland and a broken foreland, where it is an area dominated first by if you look previous studies in the area in heat flow, we can mention Henry and Pollack in 1988. We identify in the back arc between 400 and 600 kilometers far from the trench, a high heat flow in the Central Andes in comparison with Peru, where we have a shallow subduction, and then the works of Springer and Foster and Springer, which also identify in the Altiplano and Eastern Cordillera a high heat flow, and they hypothesize an asthenospheric wedge. Then Ziemlowski identify low velocity in this area and define the APEN, the Altiplano Puna magmatic body, which Hamza, Ibarra, and Christensen also modellate in the heat flow regional models with more data in the last studies. Here is the basin located. So the basin is a wide syncline, limited from the west and the east for ranges. In the east, we have the Santa Barbara Range, and in the west, we have the Zapla Cerro Amarillo Range. This area is characterized by it's a subtropical climate with a lot of industry, mainly industry of sugar, cane. And we start to investigate this area because there are a lot of hot springs with different temperatures, as you can see here. And our target was the Chacorite Formation. It's a unit limestone from the Cretaceous Rift, which was associated with oil, like an oil reservoir. And it, in the exploratory oil and gas wells in the area was not successfully for the hydrocarbon production, but they identify a lot of confined aquifers in this unit. So the workflow we applied to estimate the geothermal potential has three branches: the heat flow branch from the thermal gradient and the thermal conductivity. And the data to estimate this we use was the borehole reports, the VH borehole temperatures and DST, and also the well logs to estimate the thermal conductivity. Then the second branch to understand the structure and the migration path flows was in the base of the seismic lines mainly, and surface information. And the third branch is the reservoir characterizations, also from the well logs and the hot springs. Well, as we are in the heat flow day, I'm going to talk about the heat flow branch. To make the temperature database, well, we analyze a lot of borehole reports, very old, from 1930 to 1990. We read all the temperatures contained in these reports and applies the Wappler's borehole correction. We look, we see an increase of the temperature around 21% after apply this correction. And with that, we make 21 individual gradients for different wells. Here in the south, for example, in the northeast and the northwestern area, there are different wells. It's interesting here to see, for example, in the northeast area, that we have an input of fresh water between 500 and 1,000 meters below sea level. And gradients, one from the surface to approximately 3,500 meters, and then we have an increase in the geothermal gradient. With all this information, we make gradient maps for the basin. Here, the A is the gradient map, geothermal map, the geothermal gradient map of the basin, where you can see in the south the temperatures, the higher temperatures around 400 degrees per kilometers. An area in the center with the lowest geothermal gradients, and an increase, particularly by fracturation of the reservoirs and a lot of free circulation in the another area. And here in the B map, we have the temperature of Chacorite Formation, and it's interesting to see here that we have this northwest, so this line, which mark a transition not only in the geothermal gradient, a change in the geothermal gradient, but also in the temperature of fracture formation that is related to the tip of the unit. We will talk about this later. Well, to estimate the thermal conductivity, as I told before, we haven't got direct measurements, so we try to estimate indirectly the thermal conductivity. For that, we use the equation of Fuchs and Foster and Fuchs, using the sonic and gamma ray well logs. For that, we select only the section of the well logs where on the condition that the content of limestone were more than 50%, and we estimate values between 3.5 and 4.2. There are quite high values for limestones, but despite the absence of analogous values in the region, some authors have estimated similar values. So for that, we continue with these information, these interpretations. So after that, we apply the Fourier law and make a heat flow map. Again, this heat flow map reflects a high heat flow for the area. We at first we think that it was an error, these values of heat flow, but then we start to analyze the regional variations in heat flow and the contours of this heat flow. This is the structural analysis of the basin. There are cross-section that the first three ones, some are from west to east, and the last one is from south to north. So here you can see a structural leap that is related also with this area of less heat flow, and also the more low values of thermal gradients. And also you can see the recharge area, which is in the western area of the basin, that maybe has some influence in the heat flow diminishes. Well, but now let's go down to what brings us here. What drives the heat flow? Well, heat flow variation are linked to the nature of the existing heat source, including sediment-derived heat production, upper crustal heat generation, magmatic reservoirs, and radiogenic heat productions at variable rates. The last one is maybe most impossible to discriminate here because there doesn't exist some meditions. The only thing I can say from this point is that in the south we have more presence of Paleozoic units with some uranium content, but it's not measured. Well, rapid sedimentation and boiler rates reduce heat flow, and we know also that high sediment deposition over the last 10 million years with subsidence rates, well, elevated subsidence rates in Bolivia, here in this area, is the responsible for the reduction in surface heat flow. But here in this area, we are in the transition zone, so it's true that we denote that in the areas where the thickness of the neogen Andean sedimentation is is higher, we have a reduction of heat flow, but we cannot explain the high heat flow of the basin only with that. Well, what about the magmatic reservoirs? It doesn't exist surface volcanism linked to in this area, linked to the APIM or the Altiplano Puna magmatic body. But in some recent works that we made with Maro et al. In 2021, 2023, and also now in 2025, we found some intermediate magmatic rocks very far from the trench. I think here, for example, where is the star. And we think that this is related with an expression of this Altiplano Puna magmatic body. So also the works of, like this example, the works of Ibarra shows the extension of the APMB very far from the trench. But what is driving this movement of the magmatic body so far from the trench? Well, we think that the presence of translithospheric structures like Olacapata del Toro and Lipes may act as lithospheric weak zones that facilitates magma emplacement and potentially enhance the heat flow farther east, including the San Francisco Basin. So, in synthesis, the spatial distribution of the geothermal gradient in the basin are not a consequence of conduction or heat flow only, but are significantly modulated by the dynamic interplay of structures, stratigraphy, heterogeneity, and deep fluid circulations, the regional extensive thermal anomaly, upper 80 milliwatts per square meter, suggests a significant contribution for deeper crustal or lithospheric heat flow source. The translithospheric fault system could provide a plausible mechanism for activated heat as well as magma and associated fluid transport for east in the volcanic arc. And consequently, the thermal structure of the region cannot be ascribed to a single cause. Rather, it must be regarded as an integrated system where sediment patterns, upper crustal heat production, and deep-sea magmatic and/or hydrothermal processes collectively redistribute heat. So we know that to comprove this, we need to highlight, we need these highlights, no? We need higher resolution, high flow data to fully constrain these relationships because we have a problem that is very old information we use to make all these interpretations. And just a little brave to be brave to make a preliminary geothermal potential for the Chacorite formation. We analyze using the volumetric deterministic method of Maffer and Cataldi favorable conditions in the northern of the basin, mainly in the Caimancito area, an area where we have 41 wells, exploratory wells of more of 3,000 meter depth, with temperature average 150 degrees. And we calculate and modulate in this last month the possibility or recovery around 20 years. So this is all. I hope you understand some of the presentation, and thank you.